Welcome everyone to this afternoon's talk, the CRM-Fields-PIMS prize. I think it's the premier mathematics prize in Canada, recognition of outstanding achievement. And we're very pleased to have Sir Behrend here as the latest in a distinguished list of recipients of this prize. So Behrend has received his PhD in 1991 at the University of California at Berkeley, and faculty member at the University of British Columbia since the middle 90s. Has received, mentioned here, numerous recognitions, including the Cox James Prize and the Jeffrey Williams Prize from the Canadian Mathematics Society, and was a speaker in the ICM in Seoul in 2014. Distinguished, said as research record in algebraic geometry, particularly in algebraic stacks, normal different theory, and Thomas invariance. And some of these credits, I'm sure, will appear in the talk that will give us this afternoon on algebraic stacks and algebraic.
Thank you very much for the introduction. Let me start. I'm just going to start by writing down like the main themes or the topics of my talk and some kind of summary. So, but all these words I want to explain during the talk. So, but just so you know what's going to be going on. So one point I want to make is that the inertia operator on the K group of stacks is diagonalizable the eigenprojections give some kind of partial fraction expansions of linear stacks, and the residue at q equals 1 gives counting invariance for sheaves on Calabi-Yau threefolds. But so for most of this talk, I will not assume that you know any of the meaning of any of these words, and in fact, if you do know the meaning of all these words, then you'll be very bored by this talk. And since a lot of these things are more advanced notions, I want to spend most of my time actually on an analogy. And so the analogy is so study just the K group of orbifolds. So that will be the main subject of my talk. And so let me start by talking about counting. So counting associates to a finite set the number of its elements. Right? That's counting. So now the generalization of this, a natural generalization to manifolds is the signed Euler characteristic. So that's denoted chi sub c of x. So x is a manifold, and it's defined by, well, -1 to the dimension of x times the usual Euler characteristic of x. And so this obeys some obvious counting rules. The first one I will mention. First one is is known as the scissor relations. So cut your manifold into pieces. So whenever we have a closed submanifold, Z in X a closed submanifold, then the signed Euler characteristic of X is the sum of the signed Euler characteristic of Z and the complement, the open complement. The second rule is the product rule. So if I have a product of manifolds, this is this Euler characteristic is multiplicative. So you can, using these two properties, you can actually calculate pretty much all these Euler characteristics of all manifolds. So, for example, from the first property, you can get that the empty manifold has 0. The one-point manifold is 1, right? If I multiply, if X is the one-point manifold, then I see from this property that it behaves like multiplication by 1. So this is the multiplicative unit. At least, yeah, under some mild assumptions. Maybe in general, you can take this as a normalization. What am I saying? Sorry, if right, this Euler characteristic take values in the integers is true. Okay, and so there, this follows from this axiom. Okay, here. The Euler characteristic of the real numbers, what is that? So if I have the real numbers, that is the same manifold as an open interval, which is the same, actually, well, it's a union of two intervals and a point. Right, and so I can use this first property, the scissor relations, to write this Euler characteristic of R as twice the Euler characteristic of R plus the Euler characteristic of the point, which is 1. And so I see that the Euler characteristic of R has to be minus 1. Right? You can get from this that the Euler characteristic of Rn is minus 1 to the n, and all kinds of other properties. Okay, so. Okay, another property is the division axiom, or the division property. If I have an unramified, unbounded covering, so of degree d, then you can use these properties, to locally the cover will be just a product cover, and you can deduce from that those two axioms that this is d times the Euler characteristic of y. Okay. that's a property that follows in the case of manifolds from the two main axioms 1 and 2. So I just want to mention that there's so this is just an example of a counting rule, this signed Euler characteristic, which satisfies these two properties. And so you can study in general counting rules. So there's the universal counting rule. So I define a counting rule is a map. Well, we can always denote it by pi from manifolds to some ring R, which is commutative and with unit, obeying the two rules that I wrote. And maybe for general rings, it's maybe a good idea to also put this normalization. So chi C is a counting rule with R the integers, and in fact, this is the universal counting rule. So whenever I have here's my example counting rule, the signed Euler characteristic, and here's an arbitrary one, then there's always a unique, this diagram commutes where this is the unique map. And that essentially follows from what I've tried to indicate here, that the two rules actually suffice to calculate all these numbers. Okay. Okay, that was just for manifolds. Now I want to talk about counting mathematical objects. So I take some kind of mathematical notion. My example I always want to stick with is a very elementary example, but it gives you a flavor of the general story. I will talk about triangles up to similarity. So these are supposed to be Euclidean triangles as we know them from high school or something. And they're considered equal if they're similar. So triangles up to similarity. And so I wanted to show you a picture of this. So there's a picture of all the triangles. So this is a picture of what's known as the coarse modular space of triangles. So since I'm studying triangles up to similarity, I've made them all have circumference 1. And so this set M is what I've depicted there, is a set of all triples A, B, C, and R3 such that A is less than or equal to B is less than or equal to C, and A plus B plus C is equal to 2. So that's my condition. So A, B, C are the three lengths of the sides. The circumference is 2, and this is the triangle inequality. I've labeled A the shortest and C the longest side. And then you see that these are all the triangles. So there's these isosceles triangles which are obtuse, and the ones that are acute. There's the equilateral triangles up there, and the right triangles form this line there. And then I also want to show you this. This is like a picture of the corresponding triangles. So for each point in this coarse moduli space, I have the corresponding triangle labeled. So here's just a few of them, right? Okay, so that's a picture of the coarse moduli space together with a family of triangles that it parameterizes. So this M here, it's a manifold with corners. I mean, you know, this has a boundary here and a boundary there, and then this point there, but this line down here and these two endpoints don't belong to it. So this is the modular space of triangles. If I want to count, okay, so it's not a manifold, but we can still, you know, extend this signed Euler characteristic to this case, and we get, if we wanted to count the points. So 1 comes from this big open piece here, where I forget about the isosceles triangles. Right, that's just an open disk. That's R2. Then there's these two lines here of isosceles triangles, contribute each -1. And then +1 is that equilateral triangle, and I get 0. But I want to convince you that this answer is wrong, because it doesn't take into account the symmetries of the triangles. You see, it's not just a picture of the triangles. In fact, whenever I have a continuous family of triangles, so I have some pictures that I wanted to explain. It's easier to explain these pictures. So here's two families of triangles which are parameterized by an interval. So here I start with this right triangle. I deform to this equilateral one, and then to this same one back. This one is similar to that one. And here I do the similar thing, but you know, I go to this equilateral triangle and then just sort of go back. And then, so because I start and end with the same asymmetric triangle, there's a unique way to glue these families into loops of triangles. And so if I do that, to these two things, what do I get? I get two different families. There's, on the one hand, this one, and on the other hand, there is this one here. Maybe I can show them both at the same time. So, well, I think I've got them wrong now, because this one should be over there, and this one should be over there. Now I've got them right. So when I glue this first family there, B and C get interchanged, and so I get this Mobius strip embedded in this family, in this loop of triangles. It doesn't happen here. So these two families are completely different families of triangles. One of them contains a Mobius strip, the other one doesn't. Even though point-wise they are actually the same. It's the same, right, for each point by point, they're identical. So if I look at the corresponding path in there's this thing there. And each of these families started with an right triangle, went over there to the isosceles ones and back. And so both of these families give the same map from the circle to M. Right? So this is the circle. This is S1 to M. Right? So for this so even though I have two completely different families of triangles, they give the same moduli map, and so that's bad. So this coarse modular space doesn't represent, I mean, almost represents the nature of families, but not quite. So we can do better by introducing, where is it? we introduce n. So n, and there's n. So m was just this small part down here that I was talking about before. Now I'm now I just replace this condition with A, B, C, all of them less than 1. So now I've made the whole thing bigger, and in fact, well, this is actually this is actually a what's known as a fine moduli space of labeled triangles. So so I consider triangles together with a labeling of the sides by A, B, and C, and so then A plus B plus C is equal to 2. That's still my condition that the circumference is 2, but then the triangle inequality just gives you this inequality there. And so then if I look at, well, so I can also show you these are the corresponding triangles, and so now you can see that the asymmetric triangles each appear 6 times. But the equilateral one only once. Now the so again now I can if I have a family of triangles. So for example, a family parameterized by a circle S1. Now the modular map into n is not a single-valued map, but a multi-valued map. So now the modular maps are 6-valued. So I can show you. So for example. Here's a picture of a loop of triangles. So here's a loop of triangles in M that consists completely of scalene triangles, and so this loop appears 6 times in N, and so I have a 6-valued moduli map to N. But then if I have this one here. So this is a family with a Mobius twist, as I showed you. There's a loop. So now it's still 6-valued, but there's by Mobius strips means that it's somehow a twisted 6-valued function. And then I can also so these are with the Mobius twist, and then there's also this kind of thing here. So where I've glued a family with a cyclic twist, and that has this 6-valued modular map. So this has as a consequence. So you see that this picture actually does reflect faithfully the twisted families from the untwisted families, because the nature of these multi-valued functions reflects that. So N together with these 6-valued moduli maps actually does completely describe the moduli of triangles. So this means that we have a map actually from this manifold n to M. So this is the stack of triangles up to similarity, and this is an unramified cover of degree 6. It's unramified because whenever if you have a family of triangles which is not labeled, and you label one of the triangles, the labels extend in a unique way into a neighborhood. That's one way to say that. Cover of degree 6. And so if we use this division rule here, okay, I'm getting ahead of myself. I just wanted to, so one last picture here of these triangles. So, so here this is how I think of the stack of triangles. Now, so this is supposed to be the stack of triangles as opposed to just this coarse moduli space, where here, so for every, every point represents a triangle, and we keep track of the automorphisms, so the symmetries of the triangles. Right, so we have order 2 stacky points for the isosceles triangles, and a collateral triangle has an order 6 stacky point. Okay, so orbifold count. So orbifold count of the not the coarse moduli space, but actually the stack M. So should be the Euler characteristic of n, which is 1, by this quotient rule 1/6. So that's the correct answer. It's not 0 as we got before. So for orbifolds, so axioms 1, 2, and let's maybe call this one 3. Determine this counting invariant. And in general, each object contributes 1 over the number of its automorphisms to a count. So, as an example, let me just also count. So instead of using this degree 6 cover to compute this signed Euler characteristic of the stack of triangles, let me do it by a stratification of this stack. So again, so there's the asymmetric triangles. They just form an open, something homeomorphic to an open disk, so R2, so that is 1. That's the asymmetric ones. Oh, sorry. That's the asymmetric ones, 1. Then we have an open interval, 2 open intervals of order 2 stacky points. So minus. So this should be minus 1/2 and minus 1/2 and plus 1/6 for the 1 stacky point up there. Right? These come with a minus sign because they're one-dimensional. Okay. Okay. I wanted to mention that these triangles, they're actually very closely related to one of the most important stacks in all of mathematics, namely the stack of elliptic curves. Namely, for every triangle, you can think of a triangle as 3 points in the complex plane, and then you look at the Riemann surface, which is a double cover of the plane ramified at the 3 points, and that gives you an elliptic curve. And so you get the moduli of elliptic curves. It's very, I mean, of course, you lose the reflections as a symmetry, but and you gain the sheet exchange, so it's not completely the same. But just explain, it's very similar. And if you count, if you do a similar argument for the stack of elliptic curves, which I call E, you get -1/12. But the details I'll maybe skip because I want to say other things. So the universal counting rule for orbifolds. So I want to use only axioms 1 and 2, not the division axiom, because that's sort of unnatural from my point of view. And right, if I include it, everything is determined. But if I don't include it, then so the universal counting rule for orbifolds. So is right orbifolds goes to, I just write k of orbifolds. So for every orbifold x, I get its class in k of orbifolds. So this is a free commutative ring with 1 on these symbols x for all orbifolds, subject to the two relations 1 and 2, namely the scissor relations and the product relations. And and actually, in this example, it's so okay. Let me just write this example. So this again, this moduli stack of triangles. So let's call this, which I called M. So now, not using the axiom 3, but only 1 and 2, I get that it is. Again, there's the non-stacky part, which is always just 1, that we already have from 1 and 2, and the normalization, which I sometimes forget. And then these intervals here, there's these stacky lines. So I can write this as actually the interval r times bz2, which is the notation for a stack which is 1 point with an order with an automorphism group z2. Sorry, this is plus 2 of those, and then because it's 2 of these intervals, and then we have plus bs3, a symmetry group of that one stacky point. And so by the product rule, this is -1, so the 1 minus 2 times bz2 plus bs3. Okay, and very similar arguments apply to general orbifolds. And you get that so it's free abelian group on the symbols BG for all isomorphism classes of finite groups. Yeah. Right, so you can always write every orbifold as some kind of linear combination of just groups. Okay, so let me then, I think I'm maybe done with an object and an automorphism. Then I can just take the constant family over an interval and glue it together corresponding to that automorphism to get a loop that is invisible and conversely. So that's that. And so in our example, the inertia of the modular of triangles, well, it's three kinds of automorphisms of triangles, three kinds of similarities. Namely, there's the identity, so that just gives an object with the identity, so that just gives us a copy of itself back. Then I have the disjoint union with, so now I have all the reflections. So, but the reflections only occur for isosceles triangles, and so they form an interval. So. Right, but now the pair, the pair. So an isosceles triangle together with its reflection, such a pair is again an automorphism group of order 2. And then I have BZ3. So these are the pairs triangle comma a rotation. But there's only one triangle which admits rotational symmetries, namely the equilateral one. And the pair, the equilateral triangle and a rotation pair, has only the rotations as symmetries, not the reflections anymore. So the symmetry group is now Z3, such a pair. So that's so in pictures I get this stack back, and then I have something like this. And then I have a stacky point, Z3. So that's the inertia. And by the way, just because actually I'm running short on time, so maybe I don't do all these calculations now. Okay, and I can, and this is actually the most important formula. The inertia of BG itself is G marked G with the adjoint action of G on itself. So right, because BG stands for a single object with G as automorphism group, and so here are, so these pairs are just always the same object, and it's just given by the automorphism, so the elements in G. But then the equivalence of such things is given by the adjoint action of G on G. When are two such objects? What is a symmetry of such a pair? That's given exactly by the adjoint action of G on itself. So you can. That's what it is.
Slider triangles. That should be R cross Z2, R cross BZ2.
No, it's R cross BZ2. It's a line. So this interval, and at every point I have the automorphism group Z2. So BZ2. That's as a stack. So I want to think of I as an operator now from the K group of, so the K ring of orbifolds to the K ring of orbifolds, right? So I can do that. Just map the orbifold to its inertia orbifold. And this is actually compatible with the product axiom and with the scissor relations, but it's not compatible with this quotient rule. That's why I don't want to. One of the reasons why I don't want to impose the quotient property. So. So let me just do as an example calculation. So in this K group, the element given by such a BG, I of BG. So by what I told you is G mod G, which right is so as right this map here obeys the scissor relations. I mean, so this is additive. I can write this as the sum over all the orbits. So this is orbits G. So in the class, so C of G are the classes of G, the conjugacy classes of G. So for every conjugacy class, I have this stack. Just broken this up into conjugacy classes. But then for each conjugacy class, this, all these objects in the same conjugacy class, these pairs are all isomorphic to each other, and I can replace it just by one of them, and then I get the centralizer of G. And so the central conjugacy classes play a special role. So each central conjugacy class is just equal to its own self, right? One element is its whole conjugacy class if it's central. And then the centralizer is the whole group. So I have the number of elements in the center of G times BG. And then I have plus G conjugacy classes which are not central. That's a calculation I will use. So examples. Let's say A is an abelian group. So then everything's central. So then the inertia of BA is equal to the number of elements of A times BA. So we see that BA is an eigenvector. With eigenvalue, the number of elements in A. So we immediately see that all integers are eigenvalues of I. So all positive integers of this operator on orbifolds. And all positive integers are eigenvalues. But let's see what happens with the first, the smallest non-abelian group. So think of just the stack of isosceles triangles. This is the stack, the orbifold of equilateral triangles. So as we had seen, right, this if I just look at the equilateral points, I get three parts, which also follows from this formula. So there is only one. The center consists of one element. I get BG, BS3, and then I have the three reflections, which are all conjugate to each other. Which have a centralizer Z2, and then there's the rotations, which are also conjugate to each other, and so have Z3. So what can I see? If I look at these three vectors in K, so corresponding to this group S3 and Z2 and Z3, this is invariant under I. The subspace generated by these three elements is invariant under I, and the matrix of I on the subspace is like this. So right, I apply to the first basis element, I get just the sum of the three basis elements. And then if I apply I to this basis element, I just multiply by 2, and by that I just multiply by 3, because those groups are abelian. And so I see that the shape of this matrix is like upper triangular, lower triangular, with different numbers on the diagonal. So I is diagonalizable. On the subspace. And you can write down okay, so there's these three eigenvalues, 1, 2, and 3. So I can project this element B as 3 into its do a spectral decomposition, decompose it into its sum of eigenvectors. So if pi 1 is the projection into eigenspace corresponding to eigenvalue 1, just diagonalizing this matrix explicitly, you get the following formulas. So this is some kind of strange way to decompose this B as 3, or decompose this group into eigenvectors. And so a theorem here is in fact, as I said, I from K to K is diagonalizable, where the spectrum of eigenvalues is the positive integers. And the proof is basically the same as in this example. By what I said, the whole thing K is generated by these BGs, so you just have to do it for BG, and you do this calculation. And you know what this means here, that there's a filtration preserved by I, and the filtration that you use is the filtration by number of elements in the center. This filters K, the number of elements in the center. And then, so I respects this filtration and induces multiplication by n on the corresponding piece, and that's exactly the proof. And so what happens, what you end up having to prove is just that. So if number of elements in the center of G is n, this implies that all of these have more elements in the center. So and I've proved on the one hand that this filtration is preserved, and also that on the associated graded I get multiplication by elements of the center. And the fact that that's true is just the fact that the centralizer of an element G contains the center, but it's bigger because it also contains the element G. That's the whole idea. And this is an example of it. So that is an example of the kind of theorem that I was proving, motivated by Donaldson-Thomas theory. So let me just say a few words about that. So in the algebraic case, so instead of manifolds, I'm interested in varieties over the complex numbers. They're even dimensional. I can replace the signed Euler characteristic by the Euler characteristic. Another thing for varieties, which is really different for varieties and manifolds, is that for manifolds, the scissor relations and the product property determines all the numerical counting invariants, right? Even the universal one. But in the algebraic context, it's not at all true. In fact, so prove that the Euler characteristic of C itself, the affine line, can be assigned any value consistent with the two axioms 1 and 2 and the normalization that the point is 1. Usually, so we therefore can stick with just a formal variable, and I'll use Q for the whatever. If I use whatever counting rule I use, I always write Q for the affine line. So now the goal is as I mentioned at the beginning, goal is to count things like sheaves on a manifold, and so just to give you one example of that, e.g. Vector bundles of rank 2 and degree 0 on P1. So that is a stack. These things form a stack, and I can use the counting. So the stack, after I've applied the scissor relations, actually decomposes like this. The trivial bundle has the general linear group GL2 as automorphism group, so this is really just a copy of BGL2. Actually, well, now I started it, so I better finish it. It's not difficult to calculate the automorphism group of this thing. And it's also not hard to compute. GL2 has the motive, or the motivic weight, this. Right, I have to choose two linearly independent vectors. For the first choice, I have affine space minus the origin, and then affine space minus 2 space minus the line I already chose. I can even sum this up if I want, even though that may not really make that much sense. Really, in the end, all this Dawson-Thomas theoretic counting that's being done by Conservative, Eulerman, and Joyce is really only interested in semi-stable objects and not unstable objects, which look these. So really, we should be interested in this part here more than the other part there. So of course I've used the quotient property here that BGL2 should be 1 over the motive of GL2. That's what I've used there. And of course, if I try to apply the Euler, plug in Euler characteristic, this doesn't make any sense because I can't set Euler characteristic. Usual Euler characteristic of C is, of course, 1, and I can't plug in 1 into these formulas. They don't make any sense. And so one way out would be stick with some counting invariant where Q is not specialized to numbers, but stays a formal variable. We one way out, which is, or even use the universal counting invariant, the universal, 1. So that's more like a la Kontsevich-Soibelman. But Joyce actually did associate numbers to these things, and so the idea is to take the residue at Q equals 1. So, for example, for the residue at Q equals 1 of BGL2, so this trivial rank 2 bundle, I have to compute the residue at Q equals 1 of this formula here. And if you can do that, you get -3/4. And this is actually the contribution of this bundle to the correct count in Donaldson-Thomas theory. So this is Joyce's definition of the weight. Okay, but there is a problem here because you can't just in this case it looks like okay, you can just treat this as a so the problem in general is problem is you need to actually be able to expand this stack in powers of Q minus 1, or write something like partial fraction expansions. Otherwise, this is not well defined, of course, the residue. And so need to expand so linear stacks at least. We're only interested in linear stacks here, and powers of like 1 over Q minus 1. And so the suggestion, which is due to Tom Bridgeland, is this is given by eigenprojections of the semi-simple inertia operator. So we only look at the semi-simple part of this automorphism groups. And because you always have like a C star of automorphisms of any bundle or coherent sheaf, and so as we had seen, of course, that if we apply inertia to BC star, we get the class of C star times BC star, which is Q minus 1 times BC star. And you see that Q minus 1 is an eigenvalue with BC star as eigenvector. So you see that Q minus 1 to the R are all eigenvalues just by taking products. And so the projection into the eigenspace Q minus 1, that gives rise to the residue. And this is working this all out in detail. So just a proof that this works is work in progress with a student of mine. Let me just finish by saying that it's more complicated than you may think, because it turns out that these aren't the only eigenvalues that the inertia has on linear stacks. There's other ones like Q squared minus 1 coming from twisted forms, twisted tori. But I'm out of time anyway, so let me stop here.
Can you just explain again about this residue? Why do you want to take the residue?
Well, one, I can only think of it this way. I mean, all bundles, all sheaves always have the trivial scalar multiplications, multiplication by non-zero scalars as automorphisms. And so that's sort of a trivial contribution. So maybe, naive counting would suggest that you should count these with 1 over q minus 1. But maybe you should count these just with weight 1 is the suggestion. And so in a really generic case where all your objects are asymmetric, then they would have exactly q minus 1 as C star as automorphism group. And then then taking the residue is the same thing as multiplying by q minus 1. And so in that case where everything's asymmetric, at least it's certainly, it's just that. But why in general the residue works, that's just the most natural way to generalize that thing in general. Yep.
And what does that semi-simple measure?
Where did I write this? So if, for example, if you have I applied to BG, do without classes, just I of BG, right? This is G mod G, the quotient stack of G with adjoint action on G. And now I can, then I can just restrict to the semi-simple part of the group. And then look at this quotient stack. This is the definition of I semi-simple of BG for the case of BG. And so in general, there's you can think of this inertia as a relative group scheme over the stack, and you restrict to the semi-simple part. It's actually there. There's also, it's pretty. There's also the unipotent part, and it actually turns out that the inertia operator is a product of semi-simple and unipotent one, and they commute. So in some sense, the eigen spectrum of I is completely determined by these two, and this one's, the unipotent one, is pretty easy. All the eigenvalues are powers of Q. So it's a semi-simple part, which is in some sense the interesting part.
Other questions? I'm afraid I'm not following this very well, but are some of these functions that are coming up are they related to modular forms?
I'm not sure. Not these kind. No. Now, of course, modular forms occur all over the subject, but not directly, and as I don't think these kinds of formula are special cases of modular forms.
Well, then let's thank again for